Okay, so now we're looking at our very first video on our statistics of two variables. So instead of looking at a single measurement, what we're doing is we're looking at data points or relationships between one parameter and another parameter. Okay, whether it's a relationship between height and I don't know, weight, or whether it's between, how many hours you study and a mark on your test, or in this case, the price of something, flat screen TVs, and the price of it, and then how many you sell. Obviously, the cheaper the flat screen TV, maybe more of it you'll sell, but then who knows? It could be any type of relationship. Well, we're starting with learning about how to effectively construct two variable graphs, scatter plots, which you did probably when you were in grade 9. Okay, you learned how to do scatter plots, and you probably constructed a few of them, and maybe even did a line of best fit and tried to figure out a slope and all sorts of stuff like that in your grade 9 class. But here, we are going to be looking at how to effectively draw these graphs and then determine lines of best fit that are computationally determined. Okay, so for example, in this case here, this is a linear relationship that we're looking at. Now, we call a relationship between two variables a relation or a correlation. Okay, if there is a relationship, we call it a correlation. Okay, in other words, one variable correlates with another variable. Okay, and scatter plots are designed to show a degree of correlation if it shows any type of pattern, and if so, whatever that pattern is, how closely it fits a mathematical relationship that we can come up with as a result of it. We can model with it. Okay, so scatter plots can communicate a lot of things. If we start with a linear relationship, a straight line of best fit, the simplest version out of all of them, scatter plots can communicate the strength, the direction, or what we call slope usually, or grade 9's call slope, the mathematical nature of the relationship. Is it linear, nonlinear? Is it quadratic? Is it sinusoidal? Who knows? Between two variables. Okay, and as a result, of course, create a model, and that mathematical model, which we call a linear relationship or a correlation, and a line of best fit associated with that, that all will boil together to us being able to make predictions outside of the data set and even within the data set. Okay, so before we do this, of course, we have to talk about the basic structure of a scatter plot, and this is still review from grade 9. In fact, I use this note with my grade 9s, the start of at least. So for a scatter plot, we have two variables. We've got the independent and dependent variable. Now, you probably remember the independent variable axis as the x-axis. Okay, independent variable axis. And then your dependent variable axis is your vertical axis. So your horizontal axis is independent, and your vertical axis is dependent. Okay, I prefer to call the independent variable the explanatory variable. The reason why is any equation that we create will involve inserting an x, or an independent variable, and using the value of that particular variable to help you determine or predict the value of your dependent variable. Okay, so not only do we have an independent and dependent variable, but we have an explanatory variable, a value that explains the value that responds to it, the response variable. So one variable explains the response. Okay, and as a result of that, a lot of times we call the explanatory variable the control variable, or not a control condition, but definitely the variable that is independent. In other words, we can adjust it if we want to, and then we look at how it responds, and the response is the y value, and then from that we determine the relationship. Okay, that's not always the way that it is. We don't experimentally determine someone's height and someone's weight, but we can use one to explain the other. Okay, just like, for example, if we looked at heights of individuals as a data set and use that to determine how long we should make pant legs, okay, for pants that we have in a store. Okay, well, if the variable we had data on, which was heights, then we could go ahead and use those heights in order to help us determine how many of each length of pant we need to make so that we can have the appropriate number available for our customers. Okay, so again, we have an explanatory variable, and then we have a response variable. Explanatory is here, response is here. The y responds to the x, if you remember it in that perspective. And we will be using x and y to abbreviate these. Now, first we're going to start talking about relationships or correlations. Okay, so the first relationship pattern that we're going to get used to is the simplest. It's the one that you got used to in grade 9. And then, of course, you learned about curved relationships in grade 10, and then grade 11, all kinds of relationships. But we're starting with a linear correlation, a straight line of best fit. It's always the default that we use for correlations because You'd like to think that a simple model, mathematical model, would be a great way to explain things. It isn't always the case, but it is or it isn't, okay? So we have two types of correlation. When we describe a correlation, we generally tend to describe it as either linear or nonlinear. If it can match a linear, beautiful. If it cannot match a linear, then we call it nonlinear, and then we do some more work with it later on, which we are going to do with Microsoft Excel as a tool to help us do that. Okay, so in these examples, these are patterns of docs. All of them are going to be X and Y. So again, explanatory variable and response variable, or independent variable and dependent variable. So we can always assume X and Y as our generic X, independent variable X, and a generic dependent variable Y. But you look at the pattern of these coordinates. These are relationships between an X value and a Y value. Okay, so one individual will be 1 point, and two things is what we'll measure with them. Okay, whether it's an individual person or an animal, or I don't know what it would be, some sort of parameter that we're measuring. Okay, distance and time. Okay, whatever it may be. Okay, if you see here, this is a curved relationship, and this one looks like a parabolic relationship, both of which are non-linear. We can also have no correlation, and that's a situation where we can't even sort of find, even when we circle the data, sort of summarize where it's going. It doesn't really look like it's going anywhere. This one kind of tells you that it looks like it's a bit of an exponential relationship, right? It's increasing at a fairly steady rate, or maybe even a circular, okay, or sigmoidal or conic relationship. But either way, and this of course looks a little bit more like a quadratic. It looks like that upside down U/V shape. And it could be any other types of relationships too. But we would call this nonlinear for these ones that are curved. We would call that no correlation, which can also exist. But then, of course, we would talk about actual linear correlations. Okay? When we talk about linear correlations, we have two relationships. Linear that's positive and linear that's negative. So when we have a linear correlation, it forms a straight line. It forms a cigar-shaped, okay? And in essence, a linear correlation will sort of tend to have areas in here which are vacant, in here and in here which are vacant, and as a result creating more or less a straight line path. The more that this blob here looks like a line and the less it looks like a potato, then the stronger the relay. We'll talk about that in a second, okay? Right now we have one that as X increases, Y increases, so it's a plus with a plus, so we call it a positive correlation. In other words, as X increases, Y increases. Okay, it's a positive or an increase. Okay, as one increases, the other increases. For this one, you'll notice that as X increases, as we go this way, Y actually decreases. Oops, Y decreases. Okay, and that's called, as one is positive, the other is negative, so it's called a negative correlation. Or a negative slope. Positive correlation, positive slope. And you know it is slope. Most people know it is slope. Okay? And so that's the direction of opening. So first of all, we talk about linear, these two, versus nonlinear. Okay? And then we talk about direction, positive versus negative. If it's linear, we can use positive and negative. If it's nonlinear, there may not necessarily be a positive or negative, although sometimes for exponential relationships there are. The next characteristic that we use to talk about is the strength of correlation. How clearly does it follow a straight line of best fit? This correlation here is a perfect positive. Why? Because if I draw a straight line, I'm not using a ruler, but if I draw a straight line, it's exact. It goes through every single value perfectly. Okay, hence the name perfect. Okay, now this is a perfect positive linear correlation. Perfect, because it goes through all of them. Positive, because as X increases, Y increases. And linear, because it looks like a straight line. Here, same idea. Perfect, because it goes through every single value. Negative. Oops, this is a negative. Oh, a perfect negative would look like this. I gotta fix that. A perfect negative linear correlation. Okay, would look like this, because as X increases, Y decreases. Okay? I better fix that. Anyway, here are examples of positive and negative correlations anyway. So maybe look at that when we're looking at a negative correlation. What we do, though, when we're talking about the strength of correlation is we look a little bit more carefully at it and see how closely it fits that straight line. Again, the more it looks like a straight line and the less it looks like a potato, okay, the stronger the relationship. So we actually use the word strong. So if you look here, you've got your straight line, and then you've got the dots, and they're a bit above, a bit below. They're not perfect. They're a bit above, a bit below, a bit above, a bit below. Even this one, this negative correlation. It's got a negative slope, but some points go through the line, but some points are above and some points are below. But they're all pretty close. And when you draw a circle around it, it kind of looks like a very, very narrow oval, a cigar or something like that. I don't know what you would call it. Something very narrow. We call that strong. Okay? For this one, you'll notice that the points are a little further off. Some of them could actually be on the line. Okay? But some are above and some are below. Still, there's vacancies in two locations. Okay? But really, if we draw a circle around it, it becomes a little bit more potato or leaf shaped. Okay? All right? And so we call that moderate. Moderate, another word for middle, or somewhere between strong and the next, which is weak. And in the weak, again, we've got a linear relation. We still have a vacancy in this area and this area, and in this area and this area. But, again, it's looking more and more like a potato and less and less and less like a straight line. Okay? And this, of course, would be weak. Weak. Okay? Now, again, the criteria that we use, we talk about strength, strong, moderate, weak. We talk about the nature of the relationship, linear, 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 and then we use negative or positive. Okay? There's also an example right here of no relationship. And again, we don't see the vacancy in this area and this area, or this area and this area if the relationship was going that way, because there's no correlation in that particular case. Okay? And so as a result, we've got a bunch of examples of the ways in which we describe a linear correlation, okay, in and of it existing. All right? Now, this is where I would stop with my grade 9s. Grade 9, homework, and then they go. And they draw their line of best fits by taking a ruler, plopping it on a piece of paper, trying their best to go through as many points as possible, maybe take the amount of points above and below and keep them as even as possible and do their best. But this isn't grade 9, this is grade 12. And in grade 12, we define correlation mathematically. In fact, we define moderate, weak, strong, using something called Pearson's correlation coefficient, R. Now, R can follow a scale. It can go from -1 to 1. If you notice, this is a perfect correlation. And this is a perfect correlation. This is a positive correlation, and so R is positive. This is a negative correlation, and so R is negative. The closer you are to 1, the stronger. Strong. Strong. Strong positive, strong negative, but 1, or -1, doesn't make a difference. The closer you are to 0, the more likely you are to no correlation. So this is where weak would be, an R value of 0.3. This is where moderate would be an R value of 0.8. That's moderate, and that's weak. In fact, your textbook says, okay, this actually creates a scale. It goes 0, and it goes 1, and it goes -1, and then it breaks it into thirds, quite simply. Okay, and so this is 0.33, this is -0.33, this is -0.66, this is 0.66, and this is where weak is found. Weak is found. And moderate is found in there, and strong is found in here. So the closer you are to 1, the stronger you get. The closer you are to 0, okay, the weaker you get, whether it's positive or whether it's negative. Okay? So here we've got some examples. We want to describe these relationships effectively. So first of all, it's linear. So I'm going to put linear down. And then linear correlation. Then I'm going to say is a positive or negative. Well, in this case, it looks like it's a negative. And I know because as I go this way, this goes down, negative. Okay? It's a linear correlation, it's negative, and is it strong? Well, I think, in fact, it's so strong that it's perfect. Okay, now some people will go perfect negative linear correlation. You may want to adjust the order of the words, but it's got those three criteria in here. Maybe we look at this one, we look at part E, and when we look at part E, we say, oh, well, what is that? Well, it's a little bit more potato-ish. And of course, the R value helps us decide, hey, is that potato a fat potato or a skinny potato? It's 0.86. So it's a strong, not perfect correlation, strong. Maybe moderate, but it's 0.86, so it's still quite strong. Okay, it's going to go up in this direction. It definitely looks like it's linear. Okay, so we're going to go strong. We're going to go positive. I know it's positive because it's a positive slope, whereas X increases, Y increases. And then it's going to be a linear correlation. Now, it's linear again because of the vacancies that we see there and there. If we look at this one, that's not only does it look like a potato, it looks like a cucumber or something. I don't know, cross section. Right, take-home messages, it looks like a round object, and as a result, no real correlation. If you look at the R value, it's very, very close to 0. Okay, I don't know if I would call this linear because I don't have vacancies there and there. I have vacancies there and there too. Okay, so I probably would call this either a weak linear, I guess, or no correlation whatsoever. And I can't even say linear or nonlinear or whatever because I can't quite tell. This, of course, is a positive linear correlation, very strong, almost perfect judged by the R value. This is a negative correlation. My R value is negative, but it's 0.94, which is pretty darn good. And of course, it looks very much like a cigar and not like a potato. And as a result, the vacancies here and here. Okay, then again, we would call that a strong negative linear correlation. And I have notes for you guys to look over if you want to that are a bit more perfect and figured out and so on and so forth. Okay, this of course is very definitely not linear. We don't just have vacancies here and here. This approaches into here. There's a vacancy, I suppose, here and here and here. I don't know. But either way, it definitely doesn't follow a straight line path, whatever it may be, no matter how shallow you make it. This is an example of a non-linear correlation. And then we're going to go through a process to look at nonlinear correlations and see which one is best. But we're going to start with linear relationships. Now, I mentioned to you this R value, and I mentioned to you interpreting this R value. The closer it is to 0, the weaker, and the closer it is to 1 or -1, the stronger. But we also have to be able to calculate that value. So here we have an example of how to calculate R. Now, R looks crazy, but it's not crazy. Okay, what it is a bunch of summations. Remember, this is add them all up, add them all up, add them all up, add them all up, just like we did in our video well, last unit when we were doing the summations of deviations or deviation squared or frequencies times deviations or just a summation of X, whatever it may be. Okay, now here notice that we have X's and Y's because we have two variables, X and Y, your independent and dependent variable. Okay, and you can flip these around if you want to. Okay, depending on who is dependent and who is independent. Sometimes it's obvious, sometimes it's not obvious. Okay, we have a familiar character here, n. That, of course, is a number of data points. Not the number of numbers, but it's a number of data points. Remember, 19 and 25 go together. They're connected with one individual. One individual's handspan and one individual's foot length. So as a result, there's connections between these. We can't just put the 20 off with something else. They have to be together, okay? And so we're looking at a two variable stat or a correlation. It's not going to, my n value isn't 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's not 10. And here n is equal to 5. I've got 5 data points. Now, how do I do the sum of x, y? Well, what I do is I take x beside y, which means multiply, x times y, and then I add them up. I always do this first, and then I do that. Okay, so what do I do? Well, the sum of x, y is x times y. Okay, let me get my answer key out here, because I'm not going to be able to do all this multiplication too quickly for you guys. You know, I don't want to make this video too long if I don't need to. So I've got my little cheat sheet over here, but pretend I'm using my calculator, because I could be. Okay, 19 times 25 is 475. 16 times 22 is 352. 21 times 28 is 588. You may say to yourself, why am I doing all these x times y's? Well, I want to do the summation of xy. So I have to do xy for this point, xy for this point, xy for this point, xy for this point, which is 567, and then xy for this point, which is 460. Again, I have nice, beautiful notes for you to look at rather than having to do this, but you can follow along with me while you're doing this. That's great. It's a great idea. So how do I calculate the sum of xy? Well, the sum of xy is going to be all these guys added up. So you could do some column addition if you want to. 5 and 2 is 7, and 8 is 15, and 7 is 22, and drop down the 2, carry the 2. I've already got the numbers figured out, or you can use your calculator if you want to. You don't have to go old school if you don't want to. And that's 2,442. Okay, I can't even speak. Anyway, so that's this. So that's what the number I'm going to plug in for this. And we'll go ahead and we'll do the substitution down here, but we have to do all these calculations first. Now I have to do the sum of x. Well, what's the sum of x? Well, I don't have to do anything with the x. So I just have to add them all up. And I get 97. And then I have the sum of y. So what do? I add up all the y values. And I get 125. And then x squared. Well, how do I do x squared? Well, you take the x value. Sorry, right down here, I got ahead of myself. The sum of x squared. Okay, we got to figure that out. We already know what n is. N is 5. Okay, the sum of x squared. Well, I have to square the x first, and then I add them all up. So I square the x. 19 squared is 361. 16 squared is 256. 21 squared is 441. And then 441 again, because another 21 squared. 20 squared is 400. And then how do I do the sum of x squared? I add them all up. And I get 1899. Now this one's a little bit quirky. This is the sum of x. See how it's in brackets? And then it's squared. So you do a sum of x, which we already have right here, and then you square it. So we've already got the 97 done. We'll have to square it later on when we do the calculation. Here's the sum of y squared. Okay, so I square the y. See how it's inside the brackets? I square the y, and then I add them up. So I take 25 and I square it, and I get 625. And I take 22 and I square it, and I get 484. And I take 28 and I square it, and I get 784. I take 27 and I square it, and I get 729. I take 23 and I square it, and I get 529. And I add all those up to get the sum of y squared, and I get 3151. Now, the sum of y and then squared, well, I just take the sum of y for this one. That's that over there. And then I square it afterwards. And we're going to sub it into the formula together. We're going to do it step by step. Okay, because this formula is a little crazy. Okay, so we go r is equal to big, long divisor. Okay, and we write down n, which is 5. And use brackets when you substitute. It's really important to use brackets. 2442. Okay, minus the sum of x, which is 97. Again, these are all sums down here of x. And then the sum of y, that's y, summed up, 125. Okay, now the denominator is the one that's a bit more complicated. Okay, it's got two brackets, two factors in there. So first we do square bracket over here. Okay, all underneath the hood of the square root. So we go the sum of x squared times n. So n is 5. Sum of x squared, so that's x squared, 1899. Minus, and then the sum of x squared. And I'm just going to go put a little squared there. We're not going to do it all at once. We're going to take our time, okay? Step by step. If you take your time, you're not going to go wrong when you do this, okay? Then, of course, you go n, 5, times the sum of y squared. So I got y squared summed up, 3151, minus. And then I go sum of y, which is 125, and then I square it. Okay, and I guess I can erase this. I don't really have to, but it's nice to close off your root to let yourself know that that's the end of it. Close off your bracket as well. Okay, and then you're going to go in short, little, baby steps. Do a simple multiplication. That's 12,210. Multiply these two numbers. That's 12,125. This we're going to have to still go in baby steps. It's a little ugly with my square root there. Okay, I'm going to go 5 times 1899, which is 9495, minus 97. Square that on my calculator, and I'm going to get 9409. Again, I'm taking it really slowly. Those people try to do it more quickly. If they're good with their calculators, they'll be fine. But if they're not, it could get pretty ugly pretty quickly. 5 times 3151 is going to be 15,755. 125 squared is going to be 15,625. Close that bracket too, and this closes off. And then I do 12, 210 minus 12, 125. That's not too crazy. It's just the number 85. And remember, still keep the square root. Okay, I'm going to go down to this number subtracted, which is 86. That's this. And then the second factor in there, that's going to be 130. Okay, and I know that I made it super big there, but again, it's the idea of making sure that you keep that square root sign. So my r is equal to 85 all over the root of 11,180. That's just this number times this number. My r is equal to 85 all over, and I'm just going to approximate it, but I'll leave it in my calculator, 105.73 ... And then my r value actually finally is going to be about 0.85 or so, 0.8039 ... But what we do is we keep 4 decimal places when we list any real measurement throughout this entire course. But for our r value and our squared value, we keep 4 decimal places when we do that. Okay. Now I have a section on constructing proper scatter plots, but if I was to construct a proper scatter plot, I'm not going to plot the data on this here. I've got it on your nice, beautiful sheet of paper. You can look at